Dear students, I am Kavita BS, Assistant Professor, Department of Physics of Government First Grade College, Tiptur. In this class, I will explain the molecular degrees of freedom and the law of equipartition of energy. This topic is in BSc course Physics subject, paper 3rd, Thermal Physics, Radiation and Optics 1. And this topic is in the lesson Thermal Physics of Unit 1. Let us start the session. First, I will explain degrees of freedom and then I will discuss about law of equipartition of energy. Then, degrees of freedom. Degrees of freedom of gas molecules can be defined as the number of ways in which a gas molecule can move, rotate or vibrate in a space freely. That means the number of ways in which a gas molecule can move, rotate or vibrate in a space freely represents its degrees of freedom. And these degrees of freedom of gas molecules can also be defined as the total number of independent variables which are required to specify the state of motion of gas molecules completely. That is, these degrees of freedom of gas molecules describes the state of motion of gas molecules completely, and these are independent variables. The degrees of freedom of gas molecules can be divided into three types. They are translational, rotational and vibrational degrees of freedom. And each type of degrees of freedom of gas molecule depends upon the number of atoms in the gas molecules and also the geometry of the gas molecules. And the degrees of freedom of gas molecules helps us to describe how a gas molecule is able to contain and distribute its energy, and also from these degrees of freedom we can estimate the values of various thermodynamic variables using law of equipartition of energy. Here the thermodynamic variables are pressure, volume, temperature, energy, enthalpy and entropy. These are the thermodynamic variables. We can calculate the values of these thermodynamic variables using law of equipartition of energy. Next, we will discuss about different types of degrees of freedom. First one, translational degrees of freedom. To explain the translational degrees of freedom, let us consider a molecule which is in three-dimensional space. Then a gas molecule which is in three-dimensional space, which is free to move in all the directions of three-dimensional space, that is along x, y and z directions. Here x, y and z axes are three mutually perpendicular directions, three mutually perpendicular axes. Then in this case the gas molecule is free to move in all the three mutually perpendicular axes. Hence, the translational degrees of freedom of gas molecules must be equal to 3. Here, the number 3 represents the total number of translational degrees of freedom of gas molecules, and it is same for all type of gas molecules. That means whether the gas is monoatomic, diatomic or polyatomic, the translational degrees of freedom is equal to 3 only. This tells that a molecule which is any type, that means it is whether it is monoatomic, diatomic or polyatomic, and it is free to move in all the directions of three mutually perpendicular axes in three-dimensional space. Hence, for all type of gas molecules, the translational degrees of freedom is equal to 3. Next, second one, that is rotational degrees of freedom. Rotational degrees of freedom of gas molecules can be represented as the number of unique ways in which a gas molecule can rotate in space about its center of mass. About an axis passes through its center of mass. And for monoatomic gas molecule, the rotational degrees of freedom is equal to 0. That means monoatomic gas has single atom. Since it is monoatomic gas, it has only one atom. And the center of mass of that atom lies on the atom itself. Therefore, the rotational motion of monoatomic gas molecule will not bring any changes in a state of monoatomic gas. Hence, rotational effect is 0 for monoatomic gas molecule. Therefore, rotational degree of freedom for monoatomic gas molecule is equal to 0. For diatomic gas molecule, the rotational degrees of freedom is equal to 2. That means if we consider a diatomic gas molecule has 2 atoms and it is in a dumbbell shape. Hence, the center of mass of this diatomic gas molecule lies along any one of the axes of three mutually perpendicular directions in space. That is, if we consider the center of mass of diatomic gas molecule which lies along the z-axis, then that molecule is free to rotate about two mutually perpendicular directions, the remaining two mutually perpendicular axes, that is x and y. So, this tells that for diatomic gas molecules, the rotational degrees of freedom is 2. And for polyatomic gas molecules, the rotational degrees of freedom may be equal to 2 or 3. That depends upon the geometry of the gas molecule or the structure of the gas molecule. Then third one, that is vibrational degrees of freedom. Vibrational degrees of freedom of gas molecule can be defined as the number of unique ways in which the atom within the molecule may move relative to the one another. Such here, vibrational degrees of freedom represents the stretching of bonds or bending of bonds. That means the number of unique ways in which atom within a molecule can move relative to one another. Here, vibrational degrees of freedom represents the bending of bonds or the stretching of bonds. For monoatomic gas molecule, it is 0, and for diatomic gas molecule, the vibrational degrees of freedom may be equal to 1 or 2. That is, at the lower temperature, it is 1, and for very high temperature, the vibration degrees of freedom for diatomic molecule, it may be equal to 2 also. And for polyatomic gas molecules, we can calculate by using mathematical calculations. That is, for polyatomic gas, which is a linear shape, that means all the atoms in a linear polyatomic molecule will have in the same line, and in case of linear polyatomic molecule, the vibrational degrees of freedom is equal to 3n minus 5. Here n represents number of atoms in a gas molecule, and for non-linear polyatomic gas molecule we use 3n minus 6 formula in order to calculate the vibrational degrees of freedom. That is 3n minus 5 for linear polyatomic gas molecules and 3n minus 6 for non-linear polyatomic gas molecules. By using this formula, we can calculate the vibrational degrees of freedom for polyatomic gas molecules. These are some of the facts related to degrees of freedom, and next we will discuss about law of equipartition of energy. According to law of equipartition of energy, at thermal equilibrium, the total energy of the system is shared equally by all its degrees of freedom, and the energy associated per molecule per degree of freedom is a constant and is equal to half kT. Here K represents Boltzmann constant value and T represents the temperature of the system, absolute temperature of the system, and Boltzmann constant value is 1.38 into 10 raised to minus 23 joules per Kelvin. And this law can be proved by using kinetic theory of gases. According to kinetic theory of gases, we have PV is equal to 1 by 3 m NaC square. Here P represents pressure, V volume, m is mass of each gas molecule, Na represents Avogadro's number, and C square is the velocity of gas molecules, average velocity. Also, for 1 mole of an ideal gas, we have one more equation, that is ideal gas equation, PV is equal to RT. In these two equations, we have LHS side is equal to PV and PV. Therefore, we can equate these two equations. On equating these two equations, we get 1 by 3 m NaC square is equal to RT. And on rearranging the terms, we get mc square is equal to 3 RT by Na. Here, the ratio of R to Na, that is universal gas constant to Avogadro's number, gives Boltzmann constant value, that is K. Hence, on substituting the value of R divided by Na as K, then we get mc square is equal to 3 kT. Then finally, by dividing above equation by 2 on either side, we get half mc square is equal to 3 by 2 kT. Here, C square represents the sum of the squares of velocities of gas molecules along 3 mutually perpendicular axes. That means C square is equal to U square plus V square plus W square. Here U, V and W are the velocities of gas molecules along X, Y and Z axis respectively. And at thermal equilibrium, since we are considering the system, the gaseous system at thermal equilibrium, hence the velocity must be in all the axes, the velocities are same. That means here U square must be equal to V square and W square. Then on substituting U value in the place of V and W, then we get C square is equal to 3 U square. Then on substituting the value of C square in the previous equation, we get 1 by 2 m 3u square is equal to 3 by 2 kt. By cancelling 3 on either side of this equation, we get half mu square is equal to half kt. So this equation proves the law of equipartition of energy. That is, at a thermal equilibrium, the total energy of the system is equally shared by all its degrees of freedom, and the energy associated per molecule per degree of freedom is a constant, and that constant value is equal to half kt. Here u square represents velocity of the gas molecules along x-axis, that is half mu square, that is nothing but energy along x-axis, that is one of the degree of freedom of gas molecules. Then energy associated with that degree of freedom is equal to half kt. This is nothing but the statement of law of equipartition of energy. Hence, we can prove the law of equipartition of energy. Then this is about law of equipartition of energy, its statement and proof. Then these are the list of textbooks for your reference. Thank you.